Look at section 7.1 homework. Nonlinears. What does that mean? Why is Jason saying that? You could have squares. You could have quadratics. What else?
Logs.
You could have logarithms. What else?
Sine, cosine.
I don't know if we've seen that, but yeah, you could have trig, right? We've covered it. Trying to show. Okay, good call. I guess I could have been showing parabolas. I'm trying to a certain type of function you guys haven't named yet. Well, absolute value would be like that. Plugging in, good guess, but no. You've talked about logarithms, you've talked about trigonometric, you've talked about squares and cubes and all those guys. What haven't you talked about? There are the weird stair steps. I'm not showing you the graph, I'm showing you the function. Who has a down and an up? This. Huh? Base, power. What am I talking about? Exponential. Exponential, like e to the x or 2 to the x, right? Yeah, I was showing exponential. I was showing a little superscript. I was trying to be helpful. I guess I could have done, there it is. I don't know if you guys would have gotten that. Logarithm that way. No, exponential is this way. Remember, log that way. I think those are the only new types. You guys did bring up absolute value. That's good. You brought up higher degree polynomials like quadratics. You brought up exponentials, logs. Now I don't know if we're going to see a lot of trig. Okay, so with that, that's some stuff that could be a little bit harder now with substitution elimination. And remember, can I go back to one of the things that we saw on Friday? These were actually two examples that we had done in section 7.1, the substitution section. So why did I bring it up here? Technically in your notes, if you guys look at the very beginning of section 7.2, this is a method that always works when solving what types of systems? Linear. Always works. That doesn't mean we can't even sometimes use them though with, oh my, it was a little touchy. Doesn't mean that we can't use them for nonlinear. So I showed you in this example, hey, there were x squareds that could match up. We could use elimination. We're just going to have some extra work to do. And we solved this in section 7.1 with substitution. Or in this one, technically we could get the y's to line up. The e to the x could be on the right side with the 0, and then the y could be on the left side with the x minus y plus 1. Just remember, whenever you're adding down, you have to group like terms. So this one didn't have an x term, so 0 plus x is, or 0x plus 1x is 1x. Or it doesn't have a constant term, so 0 plus 1 is 1. But you could have eliminated the y's. But still, is there a by-hand way of solving this one?
No.
No. Sadly. If I go to get rid of the if I go to get rid of the e with an ln, I'm going to trap this x. So sadly, sometimes, oh, okay, don't worry though, the directions will tell you to use what? Yeah. Your calculator, your grapher. And how do we use the grapher again? Y equals, we get a graph of as many equations as we have, and intersection. Second trace, intersect feature, we practiced it last year. Well, hopefully you did, but last week, right? Yeah, it would have been a little while ago. But put in our y1, put in our y2, look for our intersections. Now, what's legal with elimination? We can technically switch around the order of elimination. So let's say they were to give you some nasty word problem where you had 3 equations. You could technically work with the first 2 or the first and last or the last 2. You can technically work with them in any order as you want as long as you use entire equations together. If you do choose to multiply an entire equation by a constant, you have to make sure you do both sides in every single term across all the addition and subtraction as far as distributing. Number 3 says add. You are allowed to add or technically subtract, but I'm going to say add a multiple of one equation to any other equation. You don't have to do just the first 2 or the last 2 or the first and the last. You can choose your order. But remember from the yellow box, or I'm reminding you from the yellow box, it said to make the coefficients the same but opposite. That way we can always add and we don't have to possibly get stuck with distributing the negative, because as we know, it's so easy for those negatives to get lost. Even if we get it some places that are correct, we tend to forget it other places. If we're dealing with linear, types of systems, and I'm going to put specifically linear. Now, we talked about some of them might not be linear, but just because this is the preferred method, or one of the preferred methods for solving linear systems, we're going to be seeing harder linear systems in the next section, and we're going to pretty much be doing elimination like the whole time in a very systematic way so that, well, I'll explain this so that when we get there. But let's talk about just linear for a second, okay? Just linear. Equivalent. If we have an equivalent system, that basically means that my lines are the exact same. Now, here's the struggle. Two lines can be the exact same and not look the exact same. Two lines could be the exact same and not look the exact same. And so quick heads up, if you go to do elimination, elimination will result in some sort of true statement. Some sort of true statement, but the variable is gone. So 0 equals 0, 5 equals 5, 102 equals 132. There's some sort of statement, but the variable, poof, is gone. You're like, ah! The reason the variable is gone is because it's an equivalent system. Equivalent systems, back in Algebra 1, we would talk about how the lines, if you were to graph them and if you were to get them both in y equals mx plus b, would be the exact same. If I can get it. The exact same line. So even though they might look differently because one might be in a different form or might be multiplied by some number on both sides. What'd you say, Joe? Y plus 2x equals 0 and? Yes. Yes, that would be an example. Now, really quickly, equivalent technically are consistent. So equivalent are consistent also. It's just a special name. Equivalent systems are consistent because there are solutions, but there's not just one solution. Technically, there are infinitely many solutions. Now, there might be ways of describing that infinitely many, and we definitely will in 7.3. I'm not sure if we will in 7.2. But there are infinitely many solutions because the lines will share every single point because they're basically on top of each other. Priscilla, what's up, kid? Oh, variable. I shortened it, var. So var for variable, yeah. The variable cancels out, and technically both cancel out. Both go away. Okay, consistent. Also has solutions, but this one will be finitely many solutions. If we're talking about lines, though, there's only going to be one solution on this one. Well, but if it's more than one, it's going to be equivalent. That's the best adjective. So when Joe said at least one solution, he's totally right. But if we're talking about, they either intersect in one, infinitely many, or none. Okay? So if there are infinitely many, we're going to call it equivalent for linear. And then if it's not equivalent, there's just going to be one solution, so we'll only be able to call it consistent. Consistent in this case, you are going to be able to, let's see, you can say that the lines have one intersection point. Now we know if it's nonlinear, there might be more than one intersection. If we're talking about a two-dimensional system, we're just going to have an x and a y. If we're talking about a three-dimensional system, we could have an x, a y, and a z. That's going to be more like section 7.3. So even though equivalent could be consistent because there are solutions, we call it equivalent as soon as we realize they're the same line. Consistent, we say, okay, they're not the same line, or at least if we're using this word, they're not the same line, or else we'd use that one. And they have one solution, and we can solve for it. X equals blank, y equals blank, done. Inconsistent, well, that's the other case. No solutions. And what happens if there are no solutions? There are two different ways that can happen. Either we have parallel lines, that are not equivalent, so non-equivalent parallel lines. Or, do you guys remember those lines in three-dimensional space that aren't parallel but never intersect? Yep, Joe's showing us. Remember what these were called? Not here, but here. Ooh, not perpendicular, that'd be like that. Are you thinking transversal parallel lines? No. Not parallel, but starts with an S. I'm hearing it, but I'm not scaling. S-K-E-W. Skew lines, S-K-E-W. That was rough. I thought I kept hearing it, but then I kept hearing extra words, and I was like, well, I don't know. Skew lines. Anyway, parallel lines or skew lines. It's one of those random geometry vocab words. Parallel lines or skew. Parallel, exact same slope. Skew, well, they never intersect, but it's like three-dimensional. It's hard to see those ones. But what happens when you go to solve? When you do elimination. Up here, elimination, everything goes away, but there's a true statement. Here, elimination, you end up getting solutions like x equals a number, y equals a number, or x equals a number, y equals a number, equals a number. Inconsistent, though, you go to do elimination, but you get a false statement. 0 equals 5. No, it doesn't. Okay, no solution. Right? There you go. So I'm going to do the exact same thing, that the variables cancel, but the statement that remains is false. The variables cancel in both, equivalent and inconsistent. But one leaves behind a true statement, so the answer infinitely many. They're the same line. They share the same points. Not all points in space, because it's only the on the line. So maybe there's a formulaic way of writing which points. All points are shared, but not all points in space. But this one, no solution because of the false statement. At this point, I technically do have like a application-y thing, but like I said a second ago, let's do something mathy, huh? So let's do a couple more examples. Now I'm going to pop over to your homework. I think I have it open. I don't want to do too many. Oh, that's dark. Okay, there we go. What is this, 7.2? Did anybody start homework and get stuck anywhere? I'll start there. Not really, no? Oh, okay. So what if we were to do, what's something interesting? If you guys, oh, hey, it's way zoomed in, isn't it? I apologize. Do you see where homework starts over here? Yeah. Lots of pictures. Couldn't you right now explain to me like what label you could give each of these systems without even solving? Like for instance, what would you label this one? Consistent, one solution, right? Consistent, one solution. It looks like inconsistent, no solutions. Now, is it ever possible that something looks parallel but is slightly off? Yeah. Okay, so hold on. Mathematically, yeah, you can totally look at the equations and make sure that we're good, right? So what would tell us that truly these are parallel lines and truly they will never intersect? There are a couple different ways of thinking about it. Slope? But wait a minute, I don't see the slope. Do you see the slope? Don't we have to get it into y equals mx plus b? Which we could do, right? So we could go ahead and say, all right, it looks parallel, but is it really? It could be a little bit off, and so eventually they'll intersect. Yeah, so Joe's going ahead and saying, well, we can get both things. Thanks, Joe. Careful. We could go ahead and get y by itself. So y is equal to, now careful, subtract the x, 2 minus x. So I don't know. It's up to you guys. You could multiply or divide by a negative, but has anyone ever thought of adding the y to the other side? Yeah. Because if you add the y, then you have a positive y equals, and wouldn't you subtract the x? Either way, you should end up at x minus 2. What's my m of the first one? 1, right? And then for the bottom one, yeah, but you're doing a different method. Hold on, Matthew. On the bottom one, you could add the 2x and then divide by 2, right? So if you add the 2x, positive 2 over 2 is 1. And then we have plus 5 over 2. Isn't my m still 1? Because 2 over 2 will reduce. So are these parallel? Yes. What's the final answer? No solution. But Matthew was like, well, why didn't you multiply the? He's not thinking get everything to be y equals mx plus b and ask yourself if it's parallel. He's thinking elimination. Guys, how would we make these eliminate? Multiply the first equation by 2, a positive 2, right? Because then 2x minus 2x addition says, hey, you're gone. Negative 2y plus 2y, 0 equals
9.
Is that true or false? So, no solution. Either way you look at it. Does that make sense? So 0 equals 9 is false. Therefore, we would say no solution. Or if they're parallel lines, false, because no solutions because no intersections. A couple different ways of thinking through some of these. Does that make sense? False? Good. Parallel? Good. Either way. No solutions, no intersections. Okay, so we talked about that a little bit, but what about this section in homework where it's like, haha, no pictures? Okay, so we have to look at just the equations. True. It technically says to use elimination, not that you can never use substitution. But can anybody find me a number that you're like, oh, gross, I don't want to do that? 22 and 26. I like both of them. Can we talk about both of them? Although, do you guys see the different letters down here or the fractions down there? Anyway. Okay. It's just different letters. Yeah, I agree. Let's take 22. You don't like them because of fractions. We all know. We're being honest, right? Life's too short to not be honest. Why don't you like the other one? Okay, so whether fractions or decimals, we're admitting right now we don't like them. True? Okay, so what do you think I'm trying to do? Well, maybe not make you like them, but at least be able to deal with them, right? I'm not sure in math if I'm necessarily going to be fulfilled in life if you leave this class saying, I like fractions. I mean, it's not bad. You'll at least be able to like do cooking and stuff with having recipes and doubling recipes and whatnot if you know fractions. But besides that, I'm not sure if that's exactly my purpose or my point. My purpose or my point is to try to show you hard things that someone somewhere says you're supposed to know and try to help you deal with them in a way that makes sense. Doesn't always work, but I try. Who can think of something? Now, we could do y equals, but do you guys realize their slopes are different? If their slopes are different, what does that mean? Eventually, they're going to... All right, so I have to solve. Can anybody... Why would you multiply by 4? Here's a strategy that you might want to write down. Doesn't mean you have to do this example right now with us. But a strategy when you have fractions is to multiply both sides by the common denominator. I have a 4 and I have an 8. If I were to get these all on the same side and try to get common denominators, I would go for 8ths, right? Same thing down here. I have a 4 and I have an 8. If I was to try to subtract this on the other side and get common denominators, I would once again go for 8ths. That might just make life a little easier when you distribute. Remember, have to multiply everything. 4 over 8 becomes 2, right? So 2 times 3 will be 6x plus 8y equals 1. Down here, I'm going to end up with 4 and 8, 1 and 2, 18, plus, which would you rather deal with, the first or the second?
First. The first one. Because the 3 has 3.
Oh, sorry, I meant the first set of equations or the second set of equations.
Oh, the second set.
Okay, that's what I thought. I was like, all of you like the fractions? I don't get it. Okay, the second set. We like this one better, right?
Yeah.
Okay, whew, that's better. Are you guys seeing multiplying him by a negative 3?
Yeah.
Oh, okay. Is anybody seeing something weird? A second ago, you guys were like, oh yeah, they're totally different. Of course they're going to intersect, but some of you were just now thinking, wait, that's a negative 18x and a negative 24y and a negative 3. If we add that to 18x plus 24y equals 3, 0 equals 0 is true. What did we not think about? We subtracted our mx, but we didn't divide by 3. What's 9 over 4 divided by 3, or 9 over 4 times 1/3? 3/4. They were not just parallel. They are exactly the, how do I know that? true statement. So what's my answer for true statement? Infinitely many solutions. And specifically, if we wanted to go a little bit more detailed, we would say that they share all the same points. Now, all points in space? No, only the points on each line, but they share all of their points. Yeah, Joe?
I think for this one, I can people can see because the first one is just the second one divided by 3.
Some people could see that. I'm not sure everyone saw it at the beginning since I convinced all of you guys that they intersected at the very beginning. But you're right, I was a little bit mean when I convinced you all that they intersected. But you see what I did, right?
Yeah.
How did I deceive you? I was like, oh look, 3/4 and ooh, 9/4. Yep, nope, won't match. I only had you focusing on one little piece of information and not looking at the whole picture. Is there a life lesson in here? Be careful. Some people only want you to look at this part and not consider the whole, and they might get you way off track as far as your decisions or your perspective, because they have you zoom in right here and say, of course, this is the truth that should lead everything, when... Anyway, just be careful. There are deceivers out there. I apologize that I was one to you just now. Question: why don't we like the decimals? Ugh, that's okay. How do you get rid of any decimals? Multiply by 10 or 100, depending on how many decimal places you want to get rid of. How many do we want to get rid of? 2. So I'm going to be multiplying by, these are hundredths. I'm going to multiply both sides by 100. Are we okay with this? If you want another way of doing it that maybe Mr. Che would be a little more... The other way of doing this is I could rewrite this in fraction form. 5/100ths minus 3/100ths. I know you don't like it, but check it. Do you guys see why I'm multiplying everybody by 100? But the other way of thinking about it is, and I think you guys know this more from chem, with scientific notation, etc. I just need to move 2 decimal places. So I just need to multiply by 10 squared or 10 to the 100th. Sorry, 10 squared or 100. Is this system a lot better now that I have 5x minus 3y is equal to 21? And 7x plus 2y is equal to 16. Is that nicer? I can't do all your homework for you. Actually, I don't know if these are homework problems. They might be. We just randomly chose them. But don't you want to make something match?
Yeah.
Do you think I'm going to zoom in on these opposite sign ones?
I think y is easier.
I think so too. I like the negative positive. I think I'll multiply this guy by 2 and this guy by 3 and then whoosh, 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 solve. All right, cool kids. With that, let's talk about what this page is. There we go. Applications. What do we do if we have a word problem or a business problem? They're not always huge paragraphs. Sometimes they start talking about revenue and cost and profit and supply and demand. Whatever type of problem they give us with words or applications to some, how will we know if it's a system? Well, yeah, but they don't always give equations. So actually, before we go there, Joe, I'm not going to say so much 2 equations. I'm going to say, are there 2 unknowns or 3 unknowns or variables? Right. You're okay. 2 variables, 3 variables, 4 variables. How many unknowns do we have? Do they have to borrow money out of 3 different accounts? Ooh, 3 different amounts, X, Y, Z. Are they producing 2 different types of chocolates, X, Y? Are they giving out 2 different types of loans, X, Y? Anyway, what are the unknowns and how many are there? Now, if there are 2 unknowns, we better go looking for how many equations? 2. Ooh, 2, right? If there are 3 unknowns, we better go looking for 3, because from Algebra 1, we learned you need however many equations as unknowns, but they're not necessarily just going to give us equations. They could be equations. They could say, hey, guess what? This equation has to be true, and this equation has to be true. Or they could give us conditions, characteristics. I'll call them clues. they might not just give us an equation. They might say something like, you know what, the way it turned out, they ended up borrowing twice as much money at this percentage rate than this original account. But technically, is it a written out equation? No, but it is a condition that can be made into an equation that we need. So what Joe was saying when he said basically it's an equation, that's true, but we're going to have to do some mathematical translating, yeah? Taking the clues and saying, okay, so what's the equation for that? What equals what? So we're going to go looking for 2 or more equations, but they might be conditions that we have to make into the equations. And that leads us up to a word problem. Some of you are still writing. Hold on, I saw your heads pop up like, ah! Give you a little bit longer, but here we go. Chicopee, Massachusetts. Say that 10 times fast. Might not be that hard. I just like saying the word Chicopee. Okay, right? Like chickpeas, but not. Okay, Chicopee. An airplane flying into a headwind travels the 2,000-mile flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah in 4 hours and 24 minutes. That sounds like a clue. On the return flight, the airplane travels this distance in 4 hours. That sounds like a second clue. Find the airspeed of the plane, one unknown, and the speed of the wind, another unknown. Ooh. Okay. I have 2 unknowns. And I have 2 conditions or 2 clues. Let's see if we can figure this out. First unknown. What's the first thing we're trying to find? Airspeed of the plane. Second unknown. Okay, now how do we use X and Y to explain or express what the clues are telling us? But are the 2 speeds equal to 2,000 miles? Miles per hour plus miles per hour doesn't equal miles, right? Wait a minute. Wait a minute. Miles per hour. Isn't that equal to miles over hour?
Yes.
How do we get from miles per hour to miles? What would we have to multiply by? Ooh. So could I say that speed, or we call it in math rate, times time equals distance? Is that a formula that maybe somewhere you've ever seen? Yeah. Distance equals rate times time. Miles per hour times hour will get us miles. Let's use that. So the first time, they traveled 2,000 miles, going 4 hours and 24 minutes. Ooh, why did I rewrite that as 4 and 24/60? 60 minutes in an hour. Does that make sense? 4 hours and 24 minutes. I can make it 4 and 24/60. If you really want, I guess we could go to minutes, but I'm pretty sure I'm not going to check miles per minute of my speed. I think miles per hour is a little bit more common sense. What don't I know? Speed. Yeah. Wait a minute. Am I just going to use the airspeed, or wait, do these work together or work against each other?
Sometimes they work.
Okay, so wait, for the 4 hours and 24 minutes, for taking longer to go to the 2,000, do you think they're working together and helping each other, or working against each other? Okay, well, together, wouldn't that make it go faster? So I think this one they're working together, going faster, and this one they're working opposite each other. And headwind going into a headwind. The plane's trying to go here, and the wind's saying, haha, I'm slowing you down. X minus Y. It's a little bit weird. And we're saying that they're directly against each other, which isn't always necessarily the case, but we don't want to go vectors, and we'll just keep them directly against each other. But then the return trip. Now, they're working together, making that 2,000-mile journey in 4 hours. Well, together, they're saying everything's constant, so the plane turns around, the wind is still blowing the same way, so now the wind is saying, hey, I'll help you go faster. You guys have had that before, right? Like you have an estimated time of arriving in a certain place and you get there earlier because the wind was helping as opposed to hurting. And there are other factors as well. It's not always just the wind that helps you get there faster. Or sometimes you're stuck on the runway for 2 hours and just sitting there. Ugh. Oh, Spirit does that? Mine was United. Anyway, we'll come back. How do we solve, guys? Elimination. Nope. Nope. You got to distribute first. Well, or we could move that to the other side. What do you guys want to do? Do you want to distribute the 4 and the 4 and 24/60ths, or do you want to divide? Let's move it. I like it. So you guys help me out just a little bit. Can someone divide 2,000 by 4 and 24/60ths? P.S. In your calculator, you can do 4 plus 24 over 60. You'll totally get what I'm talking about. So all of this leads us to the system. X minus y is equal to, what's 2,000 divided by 4 and 24/60ths? 4.54? Oh, that makes more sense. I'm like, it should be something around the hundreds. Oh, we'll stick with the decimal, but I forgot the decimal places. 454 point. Oh, it just keeps on going, huh? And then the next one is easy because 2,000 divided by 4 is 500, yeah? Why did some of your classmates, even if you didn't think so, like the idea of dividing? What is it set and prime ready to do? Elimination, yeah. It's totally ready to be eliminated because those y's gone. 2x is equal to 954.5454. All we got to do is divide both sides by 2. And we end up with 477.2727. I might be just making that up. 2 goes into 9 2 times, carry the 1, 15, that's 7 times, carry the 1, 14, that's 7 times. 2 goes into 5, 2 times, 14, 7, 2 times 7. Yeah, I think that's good, right? Long division in my head. Okay. And then y is equal to, ooh, this one's easier. 500 minus that. 22?
Yeah.
0.727?
Yeah. Yep.
You guys are totally disagreeing with me. We'll say MPH. I think so. That's a 2. That's a 2. That's an 8, but you have to take away 1, so that's a 7. That's a 3, take away 1, 2. Yeah, okay, we got it. But do you see how we even started thinking about systems? I first said, who are my unknowns? Plane speed, wind speed. Who are my equations? I don't know, I have 2 clues. Let's figure out how to put those in equations and solve. Guys, that's the end of section 7.2. Nobody else had any other questions on 7.2? Oh, no, it's okay, Lauren. What'd you miss? Oh, can I? Let me do this. Let me single page. And let me do entire page. And let me go back. There you go. There you go. This is actually kind of nice because guess what our calendar says we're supposed to do today besides finishing 7.2? Starting 7.3. However, I was totally ready to go over any homework questions you might have had by being amazing and, you know, doing the homework of, oh, you did have homework. Oh, we've talked about it all year. If your homework isn't due the next day or the next school day, what is always your homework to do? Start. Struggle. 7.3. Look at you guys, procrastinators. Just kidding. Just kidding. You had a choice. You had a choice. You had a choice. I was just ready and available for questions tomorrow. So that wasn't necessarily judgment. I realize sometimes choosing something other than getting ahead in homework is not bad. I get that. Why am I having you peek at this if we literally have like 2 minutes left of class? Because I want to show you the purpose of 7.3. These are scary. 3 equations, 3 unknowns. Stink. Some of you are like, we've done this before. Yeah, you have. And some of you are like, I have to figure out a way. Well, here's my question. Here's my question. Which one looks easier to solve, the left or the right?
Right.
All the way. Why the right? Ding, 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 ding. I got one. Back substitute. I got another one. Back. I got the last one. Guess what's true about these two? They're the exact same thing. But guess what you're going to be given in problems?
That one. The left one.
So guess what this does? Takes this, makes it into that. So boom, 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 we're done. What we're going to learn in section 7.3. How do you take this, make it into that, so boom, boom, boom. Huh. And then maybe someday you can program a computer to do it for you. Or program something else technological to solve another really cool problem that someone else could use to save them work. Anyway, matrices, that's not until chapter 8, but we're getting there. Bye, guys.